NetSim is used for the network simulation and can be used for power swing testing using the NetSim module. Normally, we was testing the power swing using the dV by dt and di by dt for the rotation relay, and we make like ramping down for the voltage and ramping up for the current until some point to create the impedance trajectory inside the impedance plane, and then we can check the feedback from the relay. For sure, the power swing it will be block the protection, distance protection, I mean. But there is a lot of types of power swings. So we have a stable power swing, we have unstable power swing, how to test it and how to differentiate between both of them. Here is the NetSim module. So if we have any distance characteristic, for example, we can open the REX, and then we can add the NetSim module inside the OCC file, just to have that quadrature shape to explain better on this quadrature shape. Now it's good. Just let me explain some slides about the power swing. So just some explanation about the difference between the power swing and out of step cases. As you can see here, we have different types of the power swing, and suppose we have the PSP inner and the outer blender. So here we have the BSD inner blender and the BSD out blender. So this power swing, which is a synchronous power swing, can result from some phenomena like loaded change, like generators and disconnector or switching actions happens in the power system, and this can be synchronous or asynchronous. So the stable power swing is synchronous, which means it returns the generator returns back to its synchronous state. So there is no out of step case. And in that case, the distance protection should be blocked and should be not read because it's a synchronous and a stable power swing case, and it's not a real fault scenario. And here you can, if you can see the two blender, you can find out from the relay protection relay manual to define the inner and the outer blender of the power swing PSP. As you can see, and the main feature for the stable power swing case is the resistive component sign will not change through the impedance trajectory. So as you can see here, we have the R and the X axis, and the synchronous power swing is entering the impedance location or the impedance trajectory from the positive R axis, and it's returning back from the same direction. So it's not cross back, and the R sign will not change. It's remaining positive or remaining negative. The main important thing is the resistive sign will be fixed in the impedance trajectory in the stable power swing cases. Okay. The other type, which is the out of step or asynchronous power swing, this is called unstable power swing. Okay, and the main features here is the resistive component sign will change from positive sign to negative sign or vice versa. As you can see here, there is a synchronous trajectory of the PSP out of a step, and here is the synchronous power swing, and both of them have time for blocking and time for tripping inside the protection relay, and it can be tested using the NetSim module. Okay. Yeah, this is the time of the TOSCP and the TOSCT. This defining the trajectory direction besides the rate of impedance threshold, and this is exactly the time between crossing the outer and the inner blender, and it's possible to distinguish between short circuit and power swings. So for the synchronous power swing test case, we have some of test cases can be implemented inside the NetSim module. So the first case, we can add a synchronous or a stable power swing. So it will simulate a pre-fault and synchronous power swing and post-fault to check the blocking of distance protection. Yeah. So in the as we explained in the first slide, you can add this test case to simulate such kind of stable power swing. As you can see here from the impedance plan or the impedance view, this is the power swing trajectory entering to the impedance plane and returning back from the same direction. So the R change, the R sign doesn't change. Okay, so as you can see here from the time signal view, here is the R and the X, and as you can see here is the positive R, negative R. So it's entering the value from minus R and exiting the reach again from the minus R. So the R sign is still not change, still the same sign. Okay, and this is the features of the stable power swing. Okay. And in this part, we will explain more about the pre-fault and post-fault, the slip angle of the oscillation, which represents the angle difference between the sending and the receiving source, which is ES and ER, and also the delta V, the delta phi. It can be specified here, delta V, delta phi impact, to check the impact of on the impedance trajectory. Okay, this is the first test case. We have also a second test case, which is a synchronous power swing using the multi-turn test case inside the NetSim module. And the multi-turn, as you can see, we have here two turn of the voltage, and here is the current. So the voltage is decaying by the time, and in the same time the current is increasing. And this is what we simulate before using the state sequencer to ramp down the voltage and ramping up the current to make impedance trajectory in a manual mode to enter the zone 1 or zone 2 to check the effect of this power swing case. Now you can do it easily using the NetSim module without any dV by dt or di by dt, which means dz by dt in the end. So you can simulate multi-turn power swing as synchronous in that case. And as you can see from the impedance view here, the R changing the sign. So the R sign is changed from negative to positive. And if you can see here, the R, it's starting with the minus R, and after this time it's changing to the positive R, which means it's the trajectory coming from the left side up to the first quadrant or the right side. And this is asynchronous out or out of step test case. And also you can check the impact of the trajectory on the impedance plane. Here is another test case, which is asynchronous power swing with fault test case. So we will simulate fault at the end of the power swing to check the feedback and the response of the protection relay. So we will, in the beginning, we will simulate asynchronous power swing and with a fault test case. Okay. Here you have, as you can see from the time signal view, here is the fault. As you can see here, here is the power swing, and here is the fault. Okay. So this is a synchronous power swing with a fault in the end here. It should be blocked and should have no any trip due to this fault, because this is a stable power swing case. Okay, so the R sign it's fixed and there is no any out of step. Clear? So there is another test case. Another PowerPoint also I need to talk about it and explain it. Here is the power swing characteristic inside the protection relay manual. You can see the E1 and E2, or the E sending and E receiving, to check the effect of the synchronous or asynchronous power swing on the impedance trajectory. And also we have one effect also of the delta voltage, which is available inside the NetSim module. So if the E1 equal E2, as you can see, here is the case number 1. As you can see in figure number 2, the impedance trajectory will be approximately line. So it's approximately a horizontal line if the E1 equal the E2 and the delta V is 0. But if the E1 less than E2, which means N equal to E1 over E2, so the N in this case will be less than 1, so the delta V will be E2 minus E1, so maybe more than 20 kV as an example. So the impedance locus circular, it will look downside. It will look downside like this. Okay, so the X is a negative sign in this case. But if the delta V is in negative, which means that E1 is greater than E2, so the impedance trajectory will look upside in that case. And here is the effect of the delta V. We have also effect of the delta phi on the impedance trajectory. And if you can see, if the delta phi is 15 degrees between the E sending and E receiving sources, which means it's a normal operation or a normal load angle, so you can see it in the figure 1. In case if you have a delta phi is 90 degrees, which means the impedance locus point near the protection zone characteristic, so it's not a fault state as shown in the figure 2. But if the delta phi is 180 degrees, as shown in the figure 3, this means the impedance locus point inside the protection zone characteristic, which means the fault state as shown here in the figure 3. There is an effect also of the slip frequency on the impedance locus. as you can see here, that on the power swing tab, you can specify the parameter relating to the slip frequency and the number of slips. And as you can see here, in case number 1, if you have a slip frequency is 1 hertz, which means the frequency of the sending source is 60 hertz, for example, and the frequency of the receiving source is 59 hertz. And so the impedance locus will move from the positive sign of resistive reach to the negative sign of the resistive reach, as shown in the figure 1. Okay, and as you can see here, the resistive reach is changed from positive sign up to the negative sign. Okay, so here is the effect of the, if you have a slip frequency, 1 hertz difference between the sending end and the receiving end. But if you have in minus 1 hertz, which means the sending frequency is 60 and the receiving frequency is 61, you will find out this impedance locus trajectory, and the R sign will change it from negative to positive. Okay, so here is the impact of delta V and the delta phi and the slip frequency on the impedance trajectory, and here is the difference between the stable power swing and unstable power swing with different cases. Now I will explain here on the NetSim module, which is the main important part. So as you can see here, you can define the fault minimum pre-fault and the fault time and the post-fault time. You can also select the faulty phase line 1 to ACE, line 2 to ACE, line to line, and 3 line. And then you have to define also the line. And this line can be defined in zero sequence or positive sequence. Impedance can be defined in Z and K, can be defined R and X, or RE over R and XE over X, as we explained yesterday in the distance radio file. And you have to specify this value for the line length, line 1 or line 2. And also we have sources here. You can define the voltage and the frequency of the sending source and the receiving source, okay, to simulate this kind of stable or unstable power swing. And here is the initial state of the circuit breaker, which you can make it closed or open, and it's better to be closed to check the tripping blocking of due to the stable power swing in some test cases. So if you don't know the generation details, the generation substation details, the generator details, you cannot put it, but you can make simulation. Yeah, you can simulate. You can suppose some values just to check the blocking and the tripping of due to stable or unstable power swing. Okay, if you don't have these values. Okay, the synchronous and asynchronous, you will add it from the select test case. So for example, I will select here, we have power swing synchronous, as you can see, and there is explanation and description of this test case. So this slipping generator doesn't fall out of step, so it returns to synchronous state. Okay, here is the stable power swing, and there is the simulation between source 1 and source 2. So we can add a test case. As you can see here, here is the power swing, but it doesn't reach to the impedance trajectory. But if you change the delta V, the delta F, which is a slipping frequency, you can make it entering to this. So we can make it like 180 degree, the slip angle. Yeah, now it's entering. Yes. If you can see, it's entering now the impedance trajectory. Yes. And you can see the effect of this power swing case. Okay. And as you can see here, the R sign doesn't change, which means it's entering from the minus R direction and exiting from the minus R direction, which is the generator is still in synchronism state and it doesn't fall out of synchronism. Okay, so it's not out of step. This is the difference between stable and unstable power swing. So we can also simulate another test cases, which is asynchronous power swing. We have two cases. One of them is a multiple turn, and the other is with fault at the end. Okay, so the multiple turn here test case for the unstable power swing with a complete pull slip. So we can add this multiple turn. Yeah, if you can see now, now that the R sign is changing the direction or the from positive sign to the negative sign. Okay, so if you can make zoom. Yeah, here is the R and Y and B. Okay, it's entering to zone 1 and passing by the impedance trajectory to the other end, to the other direction, which is the second quadrant. Okay, and there is multiple turn. So you can make one turn, you can make more than one turn from here. For example, you can make two turns. As you can see, we have now two turns, and here is the voltage time signal view, and here is the current time signal view. Okay, clear? Clear. There is the impedance. You can show the impedance one per diagram or triples for the three phase, and there is for the line to ground. You can also choose for the line to line. And here is another test case. The third test case is to insert asynchronous with fault at the end. So here in the description, you will simulate test case for unstable power swing with a complete ball slip out of step. During this slip, a short circuit fault occurs. Okay, to check the effect of this unstable power swing. As you can see here, here is the power start. Here is the power swing case starting from here, and here is the fault case. Okay, so here we can simulate this kind, and also you can make it multiple turns if you like, for more realistic behavior. And the fault will be right here. Okay, so you can insert time if you need to check time, or you can insert select case, and so on. It's very simple. There is no need to calculate dV by dt, di by dt, and the rate of change of the impedance for the impedance trajectory. Just you have to enter the values of the source and source, sending source, receiving source, slip angle, delta phi between the both sources, or delta f between both sources, or delta v between the generator and the receiver and the receiving end. So you can simulate more cases using this module. It's dedicated for network simulation. It's from the name NetSim.